So I will do with you some problems to remember how to deal with heat transfer processes and how to apply them to problems involving energy transfer. A glass window of width W equals to 1 meter and height equal to 2 meter is 5 millimeters thick and has a thermal conductivity Kg equals to 1.4 watt per meter Kelvin. If the inner and outer surface temperatures of the glass are 15 degrees and minus 20 degree respectively on a cold winter day, what is the rate of heat loss through the glass? To reduce heat loss through windows, it is convenient to use a double pane construction in which adjoining panes are separated by an air space. If the spacing is 10 millimeter and the glass surfaces in contact with the air have temperatures between 10 degrees and minus 15 degrees, what is the rate of heat loss from a 1 meter times 2 meter window? The thermal conductivity of air is Ka equals to 0.024 watt per meter Kelvin. This problem is involving one of the main modes of heat transfer, which is conduction. And as application, it is a very important application in the construction field because whenever we want to select windows, we should take care of the insulation level of the windows, the conductive properties of the glass, if we have single glazing or double glazing. And the majority of our buildings has as properties double glazing because it will reduce heat losses between the indoor and outdoor environment, so we can reduce the ventilation needs, etc. So here they simplified a little bit the problem for us, but I will tell you how to deal with it in a more complex in case of more complex scenario. So first they told us if we have a single glazing, we know the thickness of the glazing. It's 5 millimeter. And we know the outer temperature is minus 20 degrees, so it's a cool day. And the inner temperature is 15. So because of the large temperature difference, we need good insulation properties for the window to avoid high heat losses. Okay. And we already know from the course material that in case of pure conduction, what we mean by pure conduction is that the only mode of heat transfer through this solid is conduction. We don't have any generation inside the window. We don't have a transient term, so everything is steady. Why it's steady? Because we are imposing constant temperatures. Yani from indoor side we have 15, from outdoor side we have the minus 20 degrees. So we can say that because we have a steady state pure conduction problem, we can say that the variation of temperature within the window is will follow the linear profile. So we have linear variation of temperature, and we know that the conduction flux, Q conduction, is given by minus K dt by dx. If we do this, this is Q second if you want, okay? This is the flux, watt per meter square. In this problem, they ask to find the heat loss, so in general, in watt. So we multiply by the area. So to get the rate, okay, of conduction, we say A times the Q second is equal to the conduction rate, Q, conduction, equals to minus K times A. So I will add the area times dt by dx. Okay. So first, for the area, we just have to know the dimensions of our window. They gave us the dimensions. It's 1 times 2, 1 meter times 2 meters. So it's 2 meters square in area. We have the glass property, the conductivity of glass is given. It's 1.4 watt per meter Kelvin. So just we still have to compute the temperature gradient. So in this figure, if you want to illustrate the direction of the flux, you know that the flux will always go from large temperature to smaller temperature. So it will move in this direction. So this is, I will take, this is my positive x, and then dt by dx will be negative because the temperature at the outer side is smaller than the inner side. That's why the flux is proportional to minus dt by dx. So when you do minus dt by dx is equal to minus of T2 minus T1 over x2 minus x1. The temperature from the outer side is minus 20. You can keep temperatures in degrees, even if here they told you watt per meter Kelvin, because we have seen that delta T in degrees is equal to delta T in Kelvin, because you know that the difference between a temperature in degree and in Kelvin is a constant. That's why, which is 273.15. So that's why delta T in degrees and delta T in Kelvin are equivalent. But please pay attention. Whenever you compute radiation, radiation is proportional to T to the power 4. You cannot keep then the temperatures in degrees. You should convert them to Kelvin to calculate the radiation flux. So here we just replace T2 by minus 20, T1 by 15, x2 minus x1 is the thickness. Also here, please pay attention for units. K is given in watt per meter Kelvin. So we should convert L here from millimeter to meter. So here it's 5 times 10 minus 3. And then you get T2 minus T1 negative, but because you have already minus before, you will get a positive conduction flux in this direction. Okay. So in this way, you can calculate the conduction of flux through this layer of your window. Now, why we use double glazing? We'll see together that by introducing double glazing will reduce a lot heat losses. What is the idea of double glazing? First, instead of one layer of glazing, we use two layers. So of course, already we have increasing thickness. So
in between.
yeah. So by increasing the thickness, yes, of course I will take in between. But now I'm just talking about glass. For glass, what we did is already we increased the thickness. Plus, we added in between an air layer. Why? Because we'll see that air is characterized by a very low conductivity. Okay, so it will reduce heat transfer between the two sides. Plus, in the course material, we'll discuss together also how to select for the spacing. Yani what should be the thickness of the spacing? You know that if you increase a lot the thickness, what can happen?
It can be bad because you'll have convection currents.
Yes, very good. If you increase a lot the thickness of air, it can be bad, because from one side it's true that we are increasing the thickness of the air layer, so we are reducing the conduction flux, but at the same time we know air is a fluid, and if you give it enough space, so if you increase a lot the air layer thickness, this will increase the freedom of particle to move, and then you can have currents of air which will lead to convective heat transfer, because we know that whenever we have a fluid moving over a surface, then we can have heat transfer by convection. That's why we can say here that this thickness should be optimized. And in the course material, we have seen a graph showing how with increased thickness, the conduction rate will be reduced, the convection rate will be increased. And then if we do the summation of heat transfer, if you want, by conduction and convection, we'll get a graph like this nearly. So you can select an optimal thickness for which heat transfer is minimized. Okay. Now, in this problem, they directly gave us, they simplified things for us. They gave us directly the temperature at the extremity of the air layer. Yani you don't need to deal with glass, but I will change the given for you to see how to do it if they just give us the extreme temperatures. To start with, if they give you for the air layer the extreme temperature, you will say the following. It's a pure conduction problem, so the conduction flux through glass will be equal to the conduction flux through air, will be equal to the conduction flux through the second layer of glass. So we can say to find the conduction rate, we can just compute what is the heat loss rate through this layer of air. Okay, and since we know the conductivity of air and we know the thickness of the space, we just have to say that Q conduction through the air layer is equal to minus conductivity of air. And you can see the difference between air conductivity and glass conductivity. The conductivity of air is much lower than glass conductivity, so you will increase the resistance of your window to heat transfer. So minus K air times the area. The area is the same. It is the cross-sectional area of the window times dt by dx. And now to compute dt by dx, you do minus 15 minus 10 over the thickness, which is 10 millimeter. We also have a considerable thickness, which is much larger than the single glazing case of 5 millimeter. So 10 times 10 minus 3. So we can see that by calculations, the conduction flux here will be reduced a lot compared to single glazing. So this is the advantage of using double glazing in our homes. Now, what if instead of giving us the temperature 10 and minus 15, what if they just gave us the inner temperature Tn and the outer temperature T out here? What can be the strategy then to calculate the conduction flux?
Generate resistance.
Exactly. One possibility is thermal resistance. Very good. Okay. I will do for you two methods to understand the concept of how we thought about the thermal resistance method. The idea is the following. If we just know the extreme temperatures T in, T out, okay, then we can say what is the governing equation. Always, whenever you have a problem of energy, you should try to do a balance for your system. To write the, if you want, what are the fluxes coming in, what are the fluxes getting out, do we have generation, do we have accumulation? So these are the questions that we should ask ourselves in order to know what to write. Here, as we mentioned, it's a steady problem. We are imposing constant temperatures, so no transient terms. We don't have any source of generation. What can be a source of generation? For example, let's say if you have a system, let's say, and inside it you have combustion. You will have generation of energy in chemical form, for example, and this chemical energy and then this chemical energy will be transferred to heat after the combustion, and this heat will be transferred through the medium, let's say by conduction. Okay, so this is an example where you have generation. Here we don't have any generation. It's a steady state case, so we can say that the temperature is linear in each material. Okay, but of course the slope of variation of temperature in glass is different than the slope of temperature in air. Why?
Different kappas.
Exactly. We have different conductance, K, and we have different thickness also. Whenever if you write the equation of energy transfer here, what can you write? You can write the following. You can write that Q conduction in glass layer 1, okay, is equal to Q conduction in air sorry, is equal to Q conduction in gas layer 2. This is the equation driving the temperature variation in your system. Okay, and then you can express each of your fluxes. You can write what is, if I call this temperature, this is Tn. Okay, this is T out. This is TR1. And this is TR2. Then I can write the following. First, if I express the conduction flux in my first layer, okay, I can write it's minus K glass times area. If you don't want to put the minus, okay, you know that heat will flow always from highest temperature to lowest temperature. So you can say that the gradient in temperature, I can say, since I know it will flow in this direction, I will just take the absolute value of delta T. So I can take T inner side minus TA1. Okay. So I can write T inner. So then I put plus because I did it in the reversed way. T inner minus TA1 over the thickness of this glass, the first glass layer. I will call it L glass 1. Okay. Equals to, in air, how you can write your flux? It's K air times the area. Now it will flow in this direction from TA1 to TA2. So times TA1 minus TA2 over L of air. And finally, this is equal to K glass times A times TA2 minus T outer over L glass 2. Okay? Now,
Doctor,
yes?
can you please repeat why did we put all of these fluxes equal to each other?
Yes, sure, I will. Okay. Okay, look. Because to understand this, okay, consider the following layer. When you say we have, if you want to look at energy transfer through this layer, do you have any generation within the glass layer, generation of energy?
No.
No. The temperatures you are imposing are constant. So do you have any variation with time?
No.
Okay. If you go back to the basic energy balance, it will tell you what? It will tell you that stored energy, okay? So let's say dE by dt of a system is equal to what? You can look if you have any if you have any generation, you can put equal E dot generation.
Plus E dot N minus E dot
Okay. Plus E dot N. This is the general energy balance that you can put for any system. Okay. Now you should look at your term. What do you have here for this layer? You don't have any generation. So this term is 0. You don't have any transient variation. So this term is also 0. You only have fluxes of energy that can come in and others that can go out. So you should ask yourself, what is the mode of heat transfer here in this problem? You have a solid, and this solid, you're exposing its surfaces to a gradient of temperature. What is the mode of heat transfer that we introduced last time that can have application here?
Conduction.
Conduction, exactly. You don't have, let's say here, you don't have a fluid moving over the surface to say that you have a convection. You don't have, let's say, if you want, you don't have, they didn't give you any input about the surfaces at different temperature, and they didn't give you emissivity to talk about radiation. You might have, of course, okay, you might have radiation, it's true, but here they just want you if you take, for example, at outer level, after when you reach, let's say, the outer surface, or when you deal of also with the inner surface, when you have exchange between the space and the indoor environment, of course you can have exchange by convection, and between the outer space and the surface you can have also convection. But here we are just interested into how heat will move through your envelope, okay, through your window. Through your window, heat can only be transferred by conduction, because you are transferring heat in a solid. For this, for air, because it's a fluid, we should pay attention to not increase a lot this thickness. So we should keep it small to have negligible convection, and then the dominant mode should be conduction. Okay, so that's why I said through this glass layer, and from this point to this one, how heat is transferred by conduction, and then from this point to this one also, because we have an optimal thickness, convection is negligible also, heat will move through, will be transferred through conduction. The same for the final layer of glass. And because you have steady cases, what will come in, if you take, let's say, this part, what is coming in air from the glass is Q conduction from glass, is equal to what is getting out from air towards the second layer, is equal to Q conduction in air. And this flux is equal to the one that will be propagated until the outdoor surface. Okay? So this is the reason why you can, your balance, your energy interpretation will tell you that the flux of conduction in the first glass layer is equal to the flux of conduction in air, is equal to the flux of conduction in the second glass layer. And now, when you write this relation, okay, you will have the following. You can write it in just you can do a small analogy, okay, from where we thought about the analogy with electricity. If you consider now your equation, you can write it in this form: delta T in glass, okay. I will just take all terms to the denominator. I will tell you why. يعني نحن كان عندنا delta T times K over L, صح? And A was simplified. So now I will take L to the denominator. Then I will have delta T glass over K glass over thickness L of the glass layer 1 equals to delta T in air divided by K air over L air equals to delta T in glass 2. So delta T glass 1 equal to delta here, equal to delta T in glass layer glass 2 over K glass over L glass 2. Now, there is a mathematical property, okay, that will tell you if you have A over B equals C over D, okay, you can add the numerators together and the denominator together, and you can say that it's equal to A plus C over B plus D. So now we can say that this is equal to, okay, delta T glass 1 plus delta T in air plus delta T in glass 2 over summation of these terms, يعني over K glass over L glass 1 plus K air over L of air plus K glass over LG2. From here, we have the idea of analogy with thermal circuit, with electrical circuit. Look why? Because here, if you replace delta TG1, what is delta TG1? T1 minus T glass 1, or T, if you want, we call it T inner, okay? So you have T inner minus T air 1 plus, what is delta T in air? It's TA1 minus TA2. So you will see that the temperatures of air will cancel out. TA1 minus TA2. And then finally, delta T in glass layer 2, it's plus TA2 minus T out. So as you can see, minus TA1 plus TA1 minus TA2 plus TA2 will cancel out. You will end up only with what? This term is equal to Tn minus T out, Tn minus T out, over summation of K over L. And we'll see together that we call these terms, so these are resistance terms. And now we'll discuss them. Okay? So, of course, in general, we add, if you add areas to all terms, we simplified area because it is the same area everywhere. Okay, but in general, you can keep an A term for all your terms. You can keep it with K, because you know that you do Ka del T over del X. So if you keep it for all terms, okay, you can, if we keep it in all terms, we can see it again, because in the conduction you have minus K times A times dt by dx. Okay. So when you write it, you can put A again for all your terms. You will not change anything because it will just be simplified. Okay, and you can put here Ka, Ka, Ka. Okay, and then you will get here Ti minus T out over sum of Ka over L. Okay, now what is the importance of doing this? When we did this analysis, we'll be able to get the conduction flux in the 3 layers without knowing the temperature of air here and here. You can directly say, I can compute the conduction flux directly from this point to this one. In order not each time to do this demonstration to see, to get the expression of the flux function of the extreme temperatures, we come up with what we call the electrical analogy. What is the idea of the electrical analogy? When we are writing our terms, we wrote delta T over a certain term, okay? That will define as resistance, now we'll see why, equal to the flux of conduction. Okay, the idea is the following. This formula is very similar to, in electricity, to delta V, which is the voltage difference, over sorry, over the electrical resistance equal to intensity of the current. Okay, so here we can do the following analogy. We can say that in heat transfer, temperature is similar in electricity to voltage, and heat rate is similar to intensity. And then we can define what we call like a thermal resistance that is equivalent to electrical resistance. To do this, to find the expression of the equivalent resistance, what we should do is to compare terms. Okay, so we know that, as we said, how we define resistance in electricity. In electricity, the electric resistance is delta V over I. Okay, so here when we did the terms together, what appeared with us is delta T over summation of terms. Each of these terms is a resistance, and the term was L, okay, over Ka. Okay, so when if you want, you can demonstrate that the resistance is of this form again by saying that let us derive R of conduction. If we go back to the formula, R of conduction should be equal to what? Should be equal to delta T over the conduction flux. Over Q conduction. Okay. And what is Q conduction by definition here? Q conduction is, if we replace it by its value, is K times A times delta T over L. So you can see here that delta L will cancel out. Sorry, delta T will cancel out. And L, you can take it to the numerator. So what is the resistance to conduction? It's L over Ka. And this is what we observed here. Here, when we did sum of T, when we summed the numerators, in the denominator, what did we get? We got sum of L over Ka. So sum of resistance to conduction. Okay, so from here we can say that by analogy with electricity, we can represent each thermal system by a electrical circuit. Okay, and here we can consider that it's equivalent to have 3 resistance in series. This is resistance 1, this is resistance 2, this is resistance 3. Okay, we can call them resistance due to glass layer 1, resistance due to glass layer 2, air layer, sorry, and this is resistance due to glass layer 2. And each resistance, because we have only here conduction here from this point to this one, we can write for each conduction, for each resistance, it's L over, so let's say for resistance in air, it's L air over K of air times A of the window. Okay, and now by analogy, instead of voltage, we need to determine delta T. Okay, or we need to relate delta T to the conduction flux. We can say that the conduction flux, which is here similar to intensity in case of an electrical circuit. Okay, so we can write, since we want to solve for Q conduction, we can simply say that Q conduction is delta T between the two extremities, which is equivalent to voltage, difference in voltage between these 2 points in the electrical circuit. So instead just of voltage 1, we have T1 or Tn inner here. And instead of V2, we have T outer here by analogy. Okay, so Q conduction will be just equal here to delta T over sum of resistances, because the resistances are placed in series. So we can write that we have T inner minus T outer over summation of resistances so directly we can directly write L glass 1 over K glass 1 times area plus L air over K air times A plus L glass 2 over K glass times A. And in this way, I can directly compute Q conduction. Once you get Q conduction, if they ask you to find now what is TR1 or TR2, you can easily do it because, as we said, the conduction flux is the same everywhere. So to get TA1, you say that I can write Q conduction inside this layer as simply as T inner minus TA1 over just, so whenever I take this layer only, Q conduction, I take the resistance here only. So over the resistance of glass 1, which is K glass, which is, sorry, L of glass over K glass 1 times A. And here L glass 1. So you know Q conduction from the previous analysis. You know T inner, it's given. You have K, L, and A. You can get TA1. Now, once you get TA1, you can apply the conduction flux between 1 and 2 in air. And finally, you can verify your result. If you apply between TA2 and T out, you get the same result. You get a Q conduction again, same value. Okay. Any question on this? Okay, yeah, we'll continue with other problems.